I want to explain, at least in the case of smooth projective varieties, a proof of the following theorem that for x over c, so a scheme of finite type over complex numbers, the category of finite étale covers is equivalent to the category of finite covariance of okay. So what do we have to check here? So so we have so I will give a proof for smooth projective x. Okay. So so maybe let me kind of, before I give a formal proof, let's see what do we actually have to show here. So we have x, okay, and we have some is a topological space, and topological, so the topological space unramified finite degree cover, and we want to show that this Z comes from a break variety scheme of C in such a way that this morphism is algebraic. So, well, we have a topological space of C points of this variety, and we want to introduce algebraic structure. We want to say what it means for a function on Z to be algebraic. Okay. So what can we do? So we can take so X is a scheme. So so we have Zariski topology. We can take Zariski open subset, and we can also look at the induced analytification. And so this will be F, and this will be F inverse of U analytic. So what kind of the goal is to define the ring of algebraic functions on this page, so that, well, this becomes a scheme. So what can we take for, what would be the natural definition of an algebraic function on this space? We know what an algebraic function here, right? It's just a function on U. But what is what would be a natural candidate for functions here?
Well, you can certainly take the ring, which is generally if a function is algebraic, it's reasonable to assume that Galois norm is algebraic over OP.
Very good idea. So let's elaborate this. So imagine that this indeed comes as analytification of some algebraic cover. Then, well, any function, algebraic function here, is integral, right? This is, well, we want to contemplate what this is, right? But, okay, so this is X is a topological space, but in fact, it's an analytic manifold, at least if X is smooth. So and this is a cover, unramified cover, so this is locally a homeomorphism, so it makes Z enter an analytic manifold. So at least we know what a holomorphic function on Z is, right? That's not enough. We want to define subring here. And the natural candidate would be just to take for this those functions that are integral, those elements here which are integral over. So we have this, and we also have we just have functions on U. And we could take for this, maybe I shouldn't have, maybe my notations are sort of confusing. So that's what you want to define. And a natural guess would be just to take the integral closure of this and this ring. So the question is why there are enough algebraic integral elements. It could be that the integral closure is this. So okay, so that was a informal remark. So let's now go back to the proof. And the proof will be based on some results of Kadaira. So I will first explain. So I will. So the strategy of the proof will be the following. So I look at this as an analytic manifold. Then this local homeomorphism makes Z into an analytic manifold, right? So we want to show that Z is actually projective. That as an analytic manifold, it can be embedded into a projective space. Then we will use a general result of Chow, saying that any analytic submanifold of projective space is actually algebraic. So in order to prove that Z is projective, we have to construct an ample line bundle. So we want to show that there exists a line bundle on Z such that which defines an embedding of Z into projective space. So a line bundle with sufficiently many holomorphic sections. And so even there is a natural candidate bundle. We can just take X analytic is assumed to be projective. So we have the ample line bundle on X. We can just pull it back. We know that pullback of an ample line bundle is, or a very ample line bundle is very ample, so it should define an embedding. Morphism is finite, yes. Yeah. So, again, the natural strategy would be just to take O1 here, pull it back, and show that this pullback defines an embedding of Z into projective space. And thus we'll complete the proof. And that's what we'll do. But again, so we need some kind of ampleness criteria. And so there is a, and that's what I will first explain. Okay. So I will start with. So a line bundle. So let Z be compact analytic manifold. Then and L holomorphic vector bundle. Line bundle, sorry. Over Z. Say that L is positive. If L has a metric whose curvature form omega is positive. Okay, so first of all, what is the curvature? So this is an element in omega 1, 1 of my Z. So this is a C infinity 1, 1 form on Z. Complex valued 1, 1 form. And what does it mean that it's positive? It means the following. So for every holomorphic tangent vector, evaluated at Z, theta bar is less than 0. Sorry, I think let me see. Let's put it by sorry. That's correct equality. Okay.
What is this form? So usually, I guess in differential geometry, you define a curvature of the canal, right?
Yes, very good question. So, so what is the, so if you, you can define a curvature of a connection. Now, every Hermitian metric, so you know in differential, so every Hermitian metric on, for every Hermitian metric on a holomorphic vector bundle, there exists a unique connection which has two properties. First of all, it preserves the Hermitian form. And secondly, it preserves the complex structure. So, so what is the connection on a vector bundle? So it's a map from sections to differential forms, and I want to write differential forms as, well, these are one forms, so I want to write it like this. It's sum of two spaces. That's a connection. In particular, so what A here stands for, well, for the space of, if you wish, C infinity sections, smooth sections of a holomorphic vector bundle. And so in particular, so this is the connection, and it has, well, it has two parts. It has, you can project it to the first component and also to the second component. So let's project it to the second component. So you get nabla 0, 1. I claim that a vector bundle with a holomorphic structure there is a canonical D-bar connection. This satisfies the Leibniz formula. It's characterized by the property that if for any holomorphic section of section S of this guy is 0. It's well defined because if you multiply a section by a holomorphic, if you take a linear, if you multiply a section by a holomorphic function, then well, this connection satisfies the Leibniz formula, but 0, 1 component of the differential of a holomorphic function is by Cauchy-Riemann equation. So, if this is true for S, it's also true for S multiplied by a holomorphic function. So now claim is that for any metric on L vector bundle with a holomorphic structure, there exists a unique nabla such that two properties hold. This part is the one above. Okay? So pick any trivialization, holomorphic local trivialization of your vector bundle. In this basis, the connection is given by the zero matrix. This is a zero map in this basis, right? Every holomorphic section goes to 0. It's not, of course, true that any section goes to 0. If you multiply your holomorphic section by a C infinity function, it gets sent to the D-bar derivative, differential C infinity function. Okay? This is the first property. And the second property is that nabla preserves the metric. So what we can hear is explanation for this sentence. Да. Да. Let's see what is the Leibniz what is the Leibniz formula for this guy. So if you take if you compute this product, it will be f times 0, 1 of S plus okay. I will write it in coordinates d f I dzi bar times dz bar times s. Okay? That's the equation. So, ну да, если функция не голоморфная. А если голоморфная, то 0. То есть, как бы утверждается, что вот голоморфная структура — это то же самое, вообще задание, ну да, что голоморфная структура, она однозначно восстанавливается вот по такой 0,1 связности. Это как бы компонента связности, вот только такая, которая содержит вот z черты. No, it's not true. It's only for the tangent bundle. There exists a unique connection, the tangent bundle, which preserves the metric. Free, yes. For a vector bundle which is not the tangent one, the notion of torsion is not defined. Does it make sense? At least, okay. So this is not a difficult claim. It's of a system of, well, it's computation. Okay. Whenever you have a line bundle, it's, well, in general, connection, the curvature of a connection is a section of endomorphism of a vector bundle with coefficients in differential 2 forms. So if your vector bundle has rank 1, it's just a 2 form. So this is a 2 form. If this condition that the connection is compatible with the holomorphic structure, this first condition, implies that the 2 form must have the curvature will be of this type. And okay, so then you can then this at least makes sense. It's happens to be a real number, and it's positive. Okay.
So on any line bundle, you can introduce an information map, right?
Yes, by using partition of unity.
Do you have any statement on how the curvature form can vary when you change the line bundle? So do you claim that if is this condition really dependent on?
Oh yes, yes. So example. So if you take say Pn and z equal to Pn and L is all 1, this is positive. This, well, you can just take on Pn the standard metric, the Fubini-Studi metric, unique one, invariant in the direction of the unitary group. Then, so this omega, well, it's called the Köhler class of this Fubini-Studi metric. It's a Riemannian, but it also can be thought as a Hermitian metric, right? Yes. So so how does it work? So this is holomorphic. And it's, you can think of this as a, so you have also, you can think of Z as a real manifold and take its tangent space as a real manifold. So this is a real vector space whose dimension is twice, real dimension is twice the dimension of this. And this holomorphic bundle sits in the complexification of this guy. And this is sort of has half, right? In other words, so if you have a holomorphic structure on a real manifold, in particular, it defines a, well, complex structure on this tangent space. So you have an endomorphism whose square is -1. And so this guy is eigenvalue, is eigenspace corresponding eigenvalue I, and you have also subspace corresponding to the eigenvalue negative. Okay? So theorem which is due to Kodaira, that if any holomorphic then n large enough to the n is generated and in this product is 0. So this is an analytic kind of part of theorem of Serre that we discussed last year. Right? So if if Z were algebraic variety, proper algebraic variety, and L were an M. So and now well, another result which is an easy corollary of this fundamental. Yes.
So
yes.
Does this theorem of Kodaira hold?
I don't know. Probably not, but I'm not sure. Good question. So if L is ample, if L is positive, then its summits then for n large enough. So this L defines an embedding of Z into the reactivization of so for well, for every line bundle which is generated by global section, you have such a map, and the claim is that this is an embedding. In particular, in particular, Z is projective. Okay? So, very good. So, this theorem, for example, is used to characterize tori, quotients of vector spaces by lattices, which are abelian varieties. So if you want to figure out, not every torus can be embedded into a projective space. So to construct an embedding, you have to construct a positive line bundle. Okay. So this kind of answers your question very close to this theorem of the second theorem of Curvature, shows that, well, if L is ample, I don't know whether it's positive, but at least a power of L is positive, right? Because it's then obtained as restriction of O1 from projective space, and that's line bundle is definitely positive. So these two numbers are very close to each other. Very good. So this is one ingredient that we are going to use, and the second ingredient is the one that I mentioned already. It's Chow, which is better than this. Well, by the way, proof is, I'm not going to explain it. It uses some Hodge theory, and the only reference, well, good reference for this, I know, is a book by Griffiths and Harris, where these two theorems are. So another ingredient is a result of Chow, which is the following. So you have category of smooth projective varieties over C. And so if you have X, you can look at its analytification, which is a holomorphic manifold. So you get a functor from this to holomorphic manifold. Manifolds. So compact. And so again, a result of Chow asserts that this is always a fully faithful functor. So any map between smooth projective varieties is necessarily algebraic. In particular, any compact holomorphic manifold has at most one algebraic structure. And this result of Curvature describes the image, the essential image of this functor, that admit a positive line bundle. Okay? So this is an equivalence of this. So now let's go back. Let's go back to the proof. Now I can easily finish it.
You stated this in a kind of tricky way. I'm not sure. Does this even really imply that?
It does, because you can take O1 and restrict it.
Well, gives X an algebraic subvariety.
No. Very good question. Suppose you have a analytic subvariety of Pn. Take O1, so it's a positive line bundle. Restriction of a positive line bundle is again positive. So you know that your variety is algebraic, yes, abstractly. So, but according to this theorem, so this functor, analytification functor, is fully faithful. So any map between algebraic varieties, in particular your variety, embeds analytically into Pn. This embedding must be algebraic.
Yeah, so modulo like the little fact that if an analytification of a map is close to embeddings, then the map itself is
yeah. Mm-hmm. Okay. Good. So proof now is very short. So again, so F is so we take X analytic, we take Z, then so we have this is F, F upper star of sits in Pn, right? So F upper star of 1. Positive, right? Why it's positive? Because just take, so we have to construct a metric on this line bundle whose curvature is positive. Just take the original metric, the pullback of the original metric, because this is an unramified cover. This is a cover. It induces isomorphism on tangent spaces. So the positivity condition, the pullback of the curvature form here will be the curvature form here, but because it's an isomorphism on tangent spaces, it means that it's positive. So that means that is algebraic. F, so it means that Z is analytification. And it's algebraic. Okay. And this gives me that direction. Why F is a tull? Because the direct image of the structure sheaf will be the structure sheaf. So it's locally free. Oh, so sorry, it will be a vector bundle.
Why? We know nothing about F, like literally nothing.
We know that it's algebraic, and it's
it's quasi-finite. That's it.
yeah. So what? So what we want to. So that means that we want to show that F of Z. What does it mean that F is flat? For finite morphisms, it just means that this is a vector bundle, right? So I want to claim, let's see whether it's that analytification of this vector bundle is, yeah, I have notation. That this is just F star of OY, of Z. That's my claim. So Y is is Z is algebraic variety. What is it? No, something wrong. No, it's okay. So, so let's see. I'm not sure that this follows formally from the result of Chow as I stated it here, but
As far as I understand, even the definition of AM for coherent sheaves requires Oca's theorem and everything else.
for finite morphisms.
For coherent sheaves.
Okay, so maybe you're right. So maybe this I formulated here only a special case of result of Chow. This is also kind of a part of, let's say, Chow theorem.
So identification commutes with arbitrary direct.
Proper direct images.
Proper direct images.
Yeah.
Well, again, we know that F identification is proper. So do you have to first prove the converse to the theorem that we discussed last time? Well, we don't know F is proper.
So we don't know that F is proper, but well, so Z is projective, right? That's what we proved. So this morphism is even projective.
Oh, so it's automatically
Yes.
finite.
Yes.
It's finite. And if we believe it's this direct image, then it's flat. And why is it italic?
Well, because fibers, because it's smooth by Jacobian criterion.
Yeah.
Okay. Very good.
Исходное утверждение про алгебраичность накрытия, оно верно для негладкого случая?
Верно. Okay.
And what is this reference for?
Background check. Okay. So now we go back to algebraic geometry, and let me explain some corollaries of what we of this deep theorem. So as I mentioned last time, even the computation of the étale fundamental group 1 minus 3 points is impossible without the theorem. There is another interesting corollary. So suppose you have x and y over C. Then canonical map, and let's say we have x bar y. Yeah, no, any. Yeah, finite type. All schemes are y of C. Then the canonical map from the fundamental étale fundamental group of the product to the product of fundamental groups is an isomorphism. So first of all, what is this canonical map? By definition, given a map to the direct product is the same as given two maps, so it's just given by projections. So, well, this is definitely true for topological spaces, for topological fundamental groups, and these are just profound completeness of those. Okay? So, remark, this is false for schemes over say FP bar, or over any other algebraically closed field of P. And let's give an example. So again, this looks like an innocent statement, but the only way to prove it that I know, that is known, is by using this analytic methods. So let's see why this is false. So let's take, let's consider A1 over FP bar. Well, first, I claim that pi1, contrary to what we could expect of A1, FP bar, yeah, well, you can take any base point, is non-zero. So I will give you an example of a finite étale cover of A1. So let's just take spec FP of let me see, T goes to spec FPX by the following formula. So X goes to e to the 5th power minus. So I claim that this is an étale cover. Finite étale. So let's check. Have to check that it's fine. Check that it's étale. That it's étale. It suffices to check tensions. Well, tensions of the residue field. So let's take. So let's see what the here A. Then the fiber. Yes, you can apply Jacobian criterion, or you can just right. So the point is that differential of this guy is equal to 1 dt minus 1. Well, the fibers is going to be just this over t to the 5th power minus t minus a. And this polynomial has no multiple roots. So it defines its disjoint union. Well, it's in fact, it's either separable extension of degree p, or it's just copies, direct product of copies of this field. Okay? So, too bad. But now I can use this example to show that the Kunet formula does not hold for A1. So I take pi1 étale of A1 times A1. And again, I'm not going to, it doesn't matter which fixed point, don't want to, I take any base points. So I will separate them in my notations. So So let's consider this map given by projections. And I claim that, well, this map is not injective. It's always injective, though, because you have sections of this projection. So well, statements about fundamental groups can be translated in the statements about finite étale covers. What does it mean in terms of finite étale covers that this map is injective? Let's try to reformulate this assertion. What do we have to construct?
I guess a non-split cover of E1 is trivial as a cover of E2.
Really? So map has a kernel. That's the assertion. So it means that there exists a
non-split cover which splits over one copy of E1.
agree. Yes? So very good. So that's equivalent to saying that there is a finite étale cover X over A2 which splits this is connected, see, which splits over A1 FP bar and point times A1 FP. Okay? Does it make sense?
Well, a finite étale cover is which means we give a finite quotient of the left-hand side.
Yes.
Such that the composition with the section, this quotient is trivial. So, now what?
So I claim that, so let's take this finite étale cover, so it gives me a finite set with an action of this group. So, and what is the property? The property is that, so this group has two subgroups, pi1 of the first copy of A1, and pi1 of the second copy, right? So let's say 0. So I know that, so these two groups act trivially on my finite set. So on the other hand, if my finite set comes from a set with an action of this group, right? So it just follows from the fact that I have a section. So that this is a section, that the composition, right? This composition is the identity.
The section is not surjective.
Yeah, yeah. Does it make sense? Okay. So now how to construct such a cover? Any idea? So the hint is, let's use Schreier equation. Very good. So take spec P bar of T, spec Fp bar of X, and let's take Fp bar of Vu, and so X is equal to Vu. Gets sent to Vu. And let's take for X the fiber product. So explicitly, you take A2 and you consider, well, you consider, so X sits inside A3, and it's given by equation T to the 5th power minus T is equal to Vu. And so this. You see that if you restrict, when V is 0, you get a split cover. When U is 0, you also get a split cover. But this cover is not split. Why it's not split?
Well, it's not generic.
Yeah. So just if P is not 2, just restrict to the diagonal, but otherwise just restrict to the generic point, right? So take the generic point of A2, so replace polynomials by rational functions, and then you get a non-trivial degree P extension of the field of rational functions in V and U. It means that the image, the fiber over, the generic fiber of this map is 1 point, is the spectrum of a degree P extension given by this equation, the splitting field of this extension, of this polynomial, right? Good. Now, so that means that this fact is trivial, and there's another interesting application. So here is a claim. Suppose I have a field K, which is algebraically closed, and which sits inside complex numbers. And I have any x over K. Then I have a map from x to from x C, which is x tensor C over K to x. And I claim that this map induces isomorphism on pi 1. Okay? So base change with respect base change, well, so you have two algebraically closed field, and then the claim is that the base change does not change the fundamental group. This is also a very deep statement, and it's false in characteristic P. So if you consider A1, and you base change from Fp bar to, say, fraction field, well, the field of rational functions, algebraic closure even of the field of rational functions here, it will change the fundamental group. So I'm not going to prove it now. This is a very good exercise. I will write it down. That's so maybe I will explain. Kind of the idea. In fact, it's so it's a corollary. Surprisingly, it's a corollary of this unit form, this property. So quite formally, you can derive this result from the property of from the first corollary. Okay, I'm going to use it now. So that means that at least subfields, algebraically closed subfields, complex numbers, we have a tool for computing the fundamental group. That's just the usual fundamental, well, profinite completion of the usual fundamental group. So let's see how it works. So before let's make the following observation. Suppose I have variety x over k. K is any field. And so a k sep will be its base change. So it's x tensor k sep over k. So this scheme has an action of the Galois group. Just because by its action on the second factor. And this action gives a action of Galois group on action. Well, this defines homomorphism from this group to the group of outer automorphisms of pi1 atal of x k sep. Right? So, so I would like to say that construction of pi1 is functorial, so any automorphism of a scheme induces an automorphism of pi1. That's not quite true, because, well, the fundamental group depends on the base point, and an automorphism does not have to preserve the base points. But still, any automorphism of x depends on automorphism of pi1 defined well up to conjugation, right? That's what we discussed last time. So for any scheme, group of automorphisms to the group of inner automorphisms, outer automorphisms of pi1. So outer automorphism is the quotient of all group of automorphisms by inner automorphisms. Okay? So let's consider an example. Let's see how it works. Okay. So let's consider for x take which is spec. Well, I'm interested in rational numbers. X inverse. So ik is q. And let's try to consider to compute the action of the Galois group of q bar over q on the fundamental of this guy. So so let's first compute pi1 et al. Of x q bar. So this is just the multiplicative a1 minus 1 point over q bar. So what do we know about the fundamental group? What? Z с крышкой. Абсолютно верно. That's because this is the profinite completion of the topological fundamental group. So we first know by the exercise that it's the same as the fundamental group of the best change to the complex numbers, right? And then by the comparison with the topological fundamental group, we know that it's z hat. But I need kind of to make this isomorphism explicit, right? I want to, in order to compute the action of the fundamental of the Galois group here, let's kind of write this sort of more explicitly. So let's consider define covers x and gm q bar. Let's consider the following system of covers x q bar. Well, that will be spec q bar y inverse, and okay, this is spec q bar x inverse, and the map is, of course, well, it takes x, y to the f bar. So we get a system of covers, and that's the system of covers is, well, it's a cofinal object in the following sense. It's an analog of the universal cover in the following precise sense. It represents the fiber factor, right? So let's take this. Let's take point 1 in GM. So it defines a fiber factor from the category of finite et al. Covers to finite sets. And we discussed that this factor for general Galois category is sort of pro-representable. It's inductive limit of representable factors. And I claim that it's pro-representable by this guy. So, so that means that pi 1 et al. Of x, which is automorphisms of the fiber factor, is actually inverse limit over n of automorphisms of these objects. So why it's pro-representable? Because it's true topologically. And we know that the analytification induces an equivalence of categories. Okay? So this is kind of a standard way of computing the fundamental group. You pick a universal cover. In topology, you pick a universal cover, and then you take the group of covariant transformations. You can do a similar thing in algebraic geometry. You can take a kind of any system of covers that represent the fiber factor, and by the way, what does it mean explicitly that this is a cofinal object? It means that if you have any cover, then there exists n such that it factors. Okay? Any connected cover, then there exists n such that it factors. And that's true because it's, again, it's not obvious if you want to prove it from scratch using only algebraic kind of algebra. It would be very hard. But it's true once you have equivalence of categorical covers. And you know that every cover of circle factors through cover of the stem. Good. So now what is this? This is what are covering transformations. So maps from this guy to this guy, which are linear over this. Just multiplication. Well, all you can do, you can multiply x by y by a root of unity. So that's limit, inverse limit of mu n, where mu n is the group of roots of unity here. So this is, so abstractly, this group is z hat. That's what we found here. But so mu n carries an action of the Galois group, the obvious action. And I claim that that's precisely the action we discussed here. So here, the group is abelian. So auto-automorphism just means all automorphisms, right? So we have an action, by this construction, we have an action of the Galois group here. And I claim that that's precisely the canonical action we have on roots of unity. So the notation for this is z hat 1, right? So Katya asked me a long time ago what 1 means here. It means that you consider this z hat as an abstract group, but you endow it with an action of the Galois group by this formula. Okay? So it might be non-trivial. And now I want to finish with one more example. So it's already non-trivial, but still it has large kernel there, this homomorphism, right? So let's take a more interesting example. Let's consider let's take for x p1 minus 3 points, 1 this, so my case is going to be rational numbers. And then, so we have the map from the Galois group of q bar over q, a very interesting group, to the group of outer automorphisms of the fundamental group, which is pi 1 of this guy, x q bar. And well, by the exercise, this is the same as the pi 1 of the complex space. And this is just outer automorphism of the profinite completion of the free group on two generators. That's because we can compare it with the topological group. So theorem, this is an injection. By the way, what is the group of automorphism of a free group in two generators? It has a special name. Everyone knows. Especially girls. Yeah, in fact, this taking automorphism does not has very little. I mean, pro-finite completion can change unpredictably, kind of. It's not at all the pro-finite completion of. It's larger than that. Yeah, much larger. So, in fact, so I will explain. Let me say a few words about the proof of this theorem. And this was a starting point of Grothendieck program. He somehow he knew that result, and he wanted to describe explicitly the image here. So he wrote a proposal applied to CNRS. His proposal was rejected, so it's never well. So the problem is still open. Describe the image. So, but now there is a kind of idea of proof. And its proof is based on theorem of Belli. What is the theorem? Belli, and that's the following statement: any for any smooth projective x over q bar, there exists a finite map to P1 Anrem et al. Over sorry, maybe I shouldn't use this twice. Over x in P1. So x is pi1 minus 3, P1 3 points. Okay? So I will not say anything about the proof of this. It's combinatorial argument. You take your curve, you first pick any cover of P1. There exists a finite map to P1. So it's, of course, it's ramified at many points. And then you play with P1. You want to compose it with another map from P1 to itself that collapse all this ramification locus of your first map, 3 points, and does not kind of produce too many additional ramification points. So, so that's kind of elementary, but it's still non-trivial. It's kind of, it's a very good topic for like first year term paper. Right, program. So it's nice mathematics, but elementary. And now the theorem, the injection, is a direct corollary of this theorem. And I will finish in 1 minute. Yeah. So, okay. So what you do, so proof of, yes, of the theorem. So pick, assume I need a name for this. Sigma is in the kernel, and it's not identity. J in Q bar such that sigma of J is not J. An elliptic curve E Q bar is J invariant equal to J. use Bernoulli theorem. So you have E, and you have a map to P1 over algebraic closure of numbers, which is unramified away from 3 points. And let's take maybe, let me see, I have two P1, and this is just spec Q bar. Okay, so let's now apply our automorphism element in the sigma. This will be spec Q bar. So it induces this map, P1 Q bar. That's also given by sigma. So this is F. And let's consider this composition. Okay? So what this diagram gives me? It gives me two covers of P1 minus 3 points, right? Because sigma maps P1 minus 3 points to P1 minus 3 points. So I get two covers. Know that they are not isomorphic, because this curve, elliptic curve, view it as a curve over Q bar, has a J invariant G. But this curve, viewed as a curve over Q bar, has invariant J invariant sigma of G. So these two, well, the same variety, but equipped with two different structure over Q bar, are not isomorphic. In particular, they are not isomorphic as schemes over P1. So that means that the Galois group, this particular element in the Galois group, acts non-trivially on the category of finite et al. Covers. And therefore, because the action of the on the fundamental group encodes its action on the category of finite et al. Covers, is also non-trivial. I'll stop here. So, questions?
So did Grotten have a precise conjecture for Wood's image?
That's a good question. So somehow he constructed many, well, a certain subgroup using the modular spaces of curves of higher genus. He constructed a subgroup in this group of outer automorphism of the free group, profane completion of the free group, where the image actually lies. So I don't think that, I'm not sure whether he actually conjectured that the image coincides with the subgroup he constructed, but probably the question, even this kind of precise question, is still open, whether the image coincides with this subgroup, rather dictator subgroup that he constructed.
Is there a question about Ivan schemes over FQ? Is there a modification which works when we want to compare Ivan product to the product of Ivans?
So that's a very good question. So there is a lemma of Drinfeld which answers this. The idea is to consider covers with an additional structure called partial Frobenius. So there is a very good talk on this by Mikhail, on this seminar by Denis Getsgori, student seminar. So I can send you a link to the video. Yeah, so there is the answer is yes, and it's very, very important and has many implications over FP. Mm-hmm. but not over kind of other fields, big fields of characteristic P. It's not known. More questions? So, well, next time, I think I need more, I want to say more about the fundamental group. We will see case, one can use this complex geometry result that we discussed at the beginning of this lecture to compute the fundamental group of varieties over a finite field by kind of reducing it to the Q bar to varieties over by lifting them in characteristic 0. So this works again only in the proper case. For example, we will describe the fundamental group of curves, smooth projective curves over Fp explicitly as a quotient of the profinite completion of the usual thing.